Okay, so it's my great pleasure to introduce the third speaker of the morning session, Tegan Emerson from PNNL, Pacific Northwest National Lab. We're going to talk about Fourier-Ring Descriptors and measuring rotational invariance for neural networks.
Thank you, and thank you for having me here. You may notice there's a slight difference in the title on my slide here versus what was written, which was actually a bit of a misnomer, measuring equivariance as opposed to invariance, which is a distinction I'll make here in a couple of slides. I will also preface this by saying this is going to be the least mathematically precise talk probably of the day in terms of equations and rigor, but I'm happy to go into more details. But
It's a long day.
yes. But as was said, I am at Pacific Northwest National Labs as my primary appointment. I'm a senior data scientist there. For those of you who don't know, all the way over here on the East Coast, this is one of the 17 Department of Energy research labs. We have a large data analytics group, and it's been a lot of fun to work there. I also hold 2 joint appointments. I'm affiliate faculty at Colorado State University in their Department of Mathematics and their Data Science Research Institute. And I also am a research assistant professor at the University of Texas, El Paso in their Department of Mathematics as well. So like all wonderful research, this was not done in isolation. I work with fantastic human beings. Dr. Timothy Doster, who is my connection to UMD originally, is one of my collaborators for this work, as well as Dr. Henry Kvinge and one of our more early career data scientists, Grayson Jorgensen. So the motivation, we're going to stay in the thread of remote sensing here, and our motivation is non-oriented imagery. And so in particular, thinking about things like overhead image analysis, maybe from satellites or others, where because we work with the government, and in particular, we work a lot with Department of Defense, and we have a lot of those types of applications, there's a lot higher risk when you build a model that can't tell the difference between something when your image is oriented one way or another. So faces, for example, there's some notion of an intrinsic orientation. When you do MRIs, things like that, there's an intrinsic orientation to your data. In overhead imaging analysis and other things like microscopy, you don't have that. And so we really want to address this issue of rotational invariance because we have high risk consequences potentially to mistakes being made by our models. So as was mentioned yesterday in a different talk, traditional convolutional neural networks break under rotation among plenty of other transformations, right? They have very brittle decision boundaries, but in particular, because rotation is one of the aspects that we're interested in for overhead imaging, what this plot is showing is the softmax output for a CNN that was trained for this image on the left. And so at the softmax output, you're getting a logit that corresponds to your roughly probability of each class. And so this is the collection of them corresponding over here. The correct one is red. And as you rotate the input image along the bottom here, you can see that it very frequently gets it wrong, right? Red is not always the highest, and there's a lot of different jumps. And so this is the type of problem that we're talking about, that just because that plane is facing a different way on the tarmac the next day, we still need to be able to say what it is with confidence. So rotational equivariance, this distinction that is the misnomer in my title here. Rotational equivariance is talking about, for model equivariance, says that essentially the output of the model is transformed according to that transformation on the input space. So to feel a little bit more like a mathematician, I did put mild-ish notation on the bottom yesterday when I started to feel insecure about this. But intuitively, right, this is just what you do. You can do the transformation and then apply your network, or you can apply your network and then you know how to transform and relate the 2 different feature maps. In this particular case, I know they're a little hard to see. This was an edge detector, for example, applied to this image of a cameraman. Invariance actually says that the output is unchanged entirely relative to that input transformation. And so here you can do the rotation, but you're always going to call it a cameraman. And so that's ultimately what we are looking to get out of our models. So in recent years, there's been a lot of study into something called group equivariant neural networks. Again, I'm not going to go into the details here, but what these do is they leverage group structure and they modify the architecture with respect to a predefined group action. So a lot of times these are the dihedral groups or the cyclic groups, which correspond to rotations. And through these mechanisms for imposing weight sharing under these different rotations, and then some sort of max pooling over the different orientations, you're actually able to get an approximately equivariant feature map invariant model coming from these modified neural network architectures. And so this was a big improvement to move in this direction. And especially because, as we said, convolutional neural networks are only approximately translationally invariant. And so it doesn't account for that. People have tried lots of different data augmentation strategies where you can include a lot of different rotations in your training data set. And they've shown that you can do comparably well with the group equivariant neural networks. The challenge here is that in practice, these actually take about 4 times as long to train with this more complex model architecture. And so we're trying to look at how can we balance between those two things, especially because so often we actually work in data limited environments. We don't have thousands of examples of every class of object that we're interested in. So this is an example of the output that you get from C8 equivariant model. So this is the cyclic group of order 8. So this is one implementation of it. And so now you can see we do get something where at least now we're always calling it the right thing. And then these periodic dips in your confidence actually correspond to when you're maximally off the appropriate rotations. So C8 would correspond to all rotations by 45 degrees. And these are all actually at 22.5 off from that. And so as you increase the order of your cyclic group, you see this curve start to flatten, which is desirable. But again, your computational time required for training goes up dramatically. So this brings us to my loose tie here to harmonic analysis. This is work I did in my master's degree, actually, for a biological application. But these are another way of constructing a rotationally invariant feature map. And so they're structured, and what they're based off of is exploiting a property of translational invariance of the amplitude spectrum of the FFT of a periodic function. So here you can see a very blurry image, but these are the types of images we work with on a regular basis of a boat. The first one is the way that it was actually collected. So we're calling that no rotation. And then if we rotate it by 90 degrees. And so a Fourier-Ring Descriptor, an FRD, is based off of sampling uniformly around concentric rings. So what I'm showing here is a single ring overlaid that's centered roughly on the boat in the middle of that picture. And then I sample the image values along that. And because I'm sampling uniformly, if I were to keep going around, I would generate a periodic function. It would repeat itself. And so as long as I rotate the underlying image with respect to that center, rotation of the underlying image induces a translation in the function, the image values along that ring. And so you can see that here in this middle figure, that if I do that 90-degree rotation for that same ring, you actually just see this translation shift. Because it's periodic, we can then compute the magnitude of the FFT here, look at the amplitude spectrum, and you get very close alignment here. Also, sort of as a side benefit, because we have symmetry, we can discard them, the second half. If we're doing it purely as features, you want to keep those if you're actually trying to do inversion, which I'll talk about. So when you are building out FRDs, in the previous slide, I just showed a single ring. But what we actually do is build out concentric rings from the center of that object. So the parameters you have to define for the construction, one of them is the actual center of the object. In practice, we've observed some sensitivity, though, as good data scientists, this can be addressed through data augmentation. So in this top, you can see where we can actually perturb the centers off from what we had previously defined. We can pick a random one in a different direction, and then we can include that in our training data set to help improve or robustify the performance there. You also have to pick the number of samples per ring. And so it's generally robust to this choice. And one of the things I'll identify in future work is that this is somewhat analogous to your choice of your cyclic group because of how you're going to be sampling uniformly with respect to arc length. And so there's going to be a connection to an actual rotation angle there as well. And then the last choice is the maximum number of rings. And this actually corresponds to the maximum spatial extent that's considered, and can be based on either the spatial resolution. If you have prior knowledge of roughly what size are the objects I'm interested in, you can use that to help set those parameter choices. One of the other things that's kind of nice about this as a property, because we're working with the amplitude spectrum, is that it is invertible. And so you can also actually reconstruct and invert and recover some notion of a template, which is what's shown in the bottom right. It is now all oriented because you're discarding the phase information when you do your recovery, but you are then able to maintain some level of explainability. And so this is an example, the original example for a use case here, where what we were trying to do was, again, in a microscopy application, and we're trying to identify circulating tumor cells and images of patient blood samples. And because they're cancer cells, you want to make sure you can call them a cancer cell regardless of their orientation. And so here on the class 1 corresponds to actual circulating tumor cells. On the right, these are marginal populations of those, and we're trying to understand what delineates them. And so what we were able to do is pair FRDs with a sparse support vector machine to identify which frequencies and which rings contained more discriminatory information. We could then invert, and we can recover some notion of where the discriminatory information is happening that can then be handed it to a pathologist, and it can be sanity checked. Would you be looking for things in this particular channel, this coloring that's happening at these different ranges? And so it was a really nice use case, and that was what motivated this work originally. Okay, so returning to this example that we have here, how do you actually compare these two different model outputs, right? There's sort of the visual inspection, which we use a lot in barcodes and persistence diagrams, as well as other metrics. But how would you actually say which one is the winner beyond that fact that this one just looks more visually appealing? And so in a recent paper, we proposed 3 new mechanisms or measures for how you capture this invariance. So the first one here is really a very practical and coarse statistic. This is the average top prediction. And so the average top prediction is essentially, for an example in my data set, so for a data point, what are the number of classes I ever call it? So at a high level, do I always call it a cargo plane, or does it get grouped into, for in that previous example, 5 different classes at some point at different rotations? And then we average over the collection of the data set. And so again, here in this example, this is with a different trained model that is, as you can see, more invariant here, but for that same cargo plane, the dominant softmax output is always cargo plane, which would make the number of top predictions for this particular example equal to 1, which is the ideal case. And so if you could do that with every example in your data set, your average top prediction would be equal to 1. So then we can move on to some slightly more fine scale relationships here. So this is the average prediction curve. And so now this is looking at how much does my actual softmax output change in consecutive rotations. So if I rotate in order sequentially, how much are they changing in a pairwise sense? And so again, trying to get the visual intuition here, what you're doing is you're computing the sum of the sequential absolute differences between each pair. And you do this actually over all of the different softmax outputs. And so again, to kind of build that intuition, the ideal case here would be a perfectly flat line at the top at 1, and everything else would be a 0, which would make the ideal score of this again equal to 0. So this is a metric where lower is better. And so then the last one is the empirical orbit variance. And so this is taking a little bit more the previous metric. I don't know why it's missing some of the notation there. But in the previous one, we're looking at this ordered sequential differences. This is just looking at the global variance of those different softmax outputs across different classes, and again, averaging. So looking at this from a visual standpoint, again, what we're doing is we're actually computing the variance of the curve here, and for all of the others, you do that, and then you average over, again, all the images in your data set. So it gives you a more holistic measure for the actual model.
So
yes.
The last one is just the variance of that collection of data points without any order. You take the average.
So you take the variance of this collection of values, and then you do it for all of the different ones that it was predicted as, and you take the sum of those, and then you average that sum across all of the images in the data set.
Oh, so it's average of variances across all these classes.
Yep. Okay, so how do we actually set up a fair comparison here? And so one of the things that we wanted to do when we were looking at FRDs as well as these equivariant models was pre-training is one of the reasons that ResNet 18 can do so well on so many things, right? And so to sort of make it a little bit more fair comparison, and because as we saw earlier in the sonar, a lot of the data that we work with doesn't look like natural imagery. And so often we actually find that pre-training doesn't help us in the same way, and in fact can introduce other failure mechanisms because of that misalignment between what our data looks like and natural data. And so for that reason, we decided that we were going to, as part of our fair comparison, do no pre-training for the neural network-based architectures. The other thing we do is all images being classified. We do what we call circle cropping with a fixed maximum radius. So this is essentially blocking out the information so that you actually get rotation of just the same content, which if you do rotation then crop from a square or rectangular setting, you have other issues and artifacts that can come through. So this is a way of trying to mitigate those and sort of make, again, the baseline fair. We did explore the performance with respect to different data augmentation strategies, so including center perturbations, as well as the rotations of the input data. We evaluated using all these invariance metrics that I just defined, as well as accuracy. And to be able to compare the FRDs to this, what we were doing is inputting them into a fully connected neural network, so that we could give the same dimension of softmax outputs and compute all the same statistics here. We looked at two different data sets. One is easier than the other one, so you always want to start with the case you might do better in, and so that would be the rare planes data set here, which has 7 aircraft classes that are a mix of sort of 2 subclasses, which are civilian and military based. We did 75-25 train test split here. And then what we did was we worked on the xView data set looking at their 9 classes of maritime vessels. And this is a lot harder in terms of what we've seen uniformly when we work with this data set. And so we wanted to see if the observations that we could make on the easier data actually translated well to the harder data set here. Okay, so the first thing that I mentioned, because for FRDs, is that you have to pick that maximum ring radius. And so how sensitive is the actual performance with respect to this? So on the left, you have some comparison of these FRDs for different numbers of rings. That's what max R indicates here. And you can see if you only do a very small number, your performance doesn't do great. You get better. There is a point at which there's maybe slightly more diminishing returns. And this is the training. So as a function of epochs, there's no data augmentation here. On the right, this is just compared, I guess, yes, right still. It's compared to a CNN, and we're doing no data augmentation. And in this case, even though it trains slower, we do actually still see that we're able to get a marginal performance gain relative to the raw images. So in this case, this might be one where it is sort of a wash if you were looking purely at the accuracy as your performance metric. So if we actually now throw in a group equivariant neural network, and so in this case, this is the cyclic group of order 4, because it's we were trying to sort of create relatively comparable training times when we were setting up this experiment. And so here you can see that this is actually now with data augmentation in the form of rotation. And the FRDs are no longer really winning out, but they're all pretty comparable, right? If we repeated this, they're statistically insignificant in terms of their performance difference in this particular case. But then it starts to become a different story when you actually look at these invariance metrics. So moving from left to right, on the left, we have that average top prediction. And so again, a perfect score of 1 would be ideal. And you can see that in that very coarse summary, the FRDs into a fully connected neural net are always lower. And so you're always actually having a better consistency in your output from your model at that sort of coarse level. If you move into the middle, which is the average prediction curve, again, you see a pretty large separation where the FRDs are winning out. And then when it comes to the empirical orbit variance, FRDs towards the end of training are still doing slightly better. But what you can tell is that, okay, yes, group equivariant neural networks do improve your actual invariance, and raw images, as we know, do the worst here. And so what we also thought about, because data science, why not just glue everything together, right? So there's a bunch of different options for doing feature fusion. And so what you can see here is that you actually do in both of these cases for the rare planes data set and the xView data set, you're able to get a performance gain by leveraging both these structured invariant features coming from FRDs, as well as learned features coming from these neural network architectures. And down along the bottom, you can actually see the different again, invariance metrics here. And what you do see is that, unsurprisingly, when you do the fusion, you're able to pull down. You're still not doing as well, but it sort of gives you a way of compromising between getting the best overall accuracy and getting invariance metrics somewhere in the middle relative to the others. So not just because this is a cool picture, classification is great. And so often, I think when you're publishing, you always start with classification as your task. But actually, a lot of what we're interested in is something like object detection in overhead imagery. We're collecting large satellite images, and we want to know what's there. And we want to be able to say what's there reliably. And so this is actually a case where what we did is we integrated a group neural network, group equivariant neural network backbone into an object detector framework. And so now as you watch these go around, you can see on the left, which is just based off of a non-equivariant object detector, that you are going to start to see there's a couple of misclassifications, and there's a lot of times where the planes just fail to be detected. Boxes disappear because of those different rotations. I think it's coming up momentarily. Yeah. And then on the right, we have this one that was trained with a group equivariant neural network backbone, and you actually maintain the presence of your boxes through all of your rotations. And so there does seem to be a strong benefit to considering these types of architectural modifications outside of just classification. One of our points of future work is there a way to also integrate FRDs, whether that's as sort of template matching or otherwise, as a mechanism for doing object detection, since that's a lot more relevant to a lot of our sponsors. And so really some of the takeaways here before I do a couple shameless plugs is that FRDs are pretty interpretable and invertible, as well as strongly invariant feature map. They can perform comparably depending on your data set, but they certainly do win out when it comes to these invariance metrics. The group, if in practice you're interested in doing this, you do see that group equivariant CNNs are more invariant, but they do come at a strong computational cost. And so it just really depends on what your trade-off there is as well. And then if you're not actually going to care about dimensionality, which as mathematicians we might, feature fusion can be a really good option as well. So again, for future work, we're looking at how can we integrate these FRDs into object detection frameworks. We also want to use these invariance metrics now as part of a penalty or part of our training routines. How can we use that? Can we actually get pretty close with even just a CNN if you appropriately modify the objective function there? And then establishing some of this theory connecting the sampling method for the FRDs to a corresponding cyclic group, and then in producing error bounds there. So the first shameless plug here is for a capability we have at Pacific Northwest National Lab. It's called tagds, Topology, Algebra, and Geometry in Data Science. We organize a series of workshops as well. We have a weekly seminar series that is run through the University of Washington. We're always looking for speakers for that. We also have an upcoming topical collection through a Springer journal, and the submission deadline is after JMM, but it is topology, algebra, and geometry in the data sciences, with the goal of trying to reduce the barrier to publishing mathematically principled approaches in the data science field, where you may not always win out over ImageNet. And so if you'd like to get added to our email list, you can send me an email here, and you can also check out our website and Twitter, which I'm trying to learn how to use. We also have a lot of different internship programs. One that I am part of and I'm happy to be a point of contact for is the National Security Internship Program. These can be done either through the school year or during the summers, and also give you a way that you can maintain working. We have a lot of students who go on to incorporate their work into their dissertation moving forward. So if you have any questions about this, please don't hesitate to reach out. We also have positions that we're always hiring for, postdocs that are more academic in nature, and then also permanent staff positions questions. These are just a few references, so I'll leave it up on this, but in particular, the paper that really develops and shows more comprehensive results outside of FRDs, which was recently accepted to the NeurIPS main track for this year, is the one that's up top. So I'm also happy to provide preprints until we get it up on archive. That I can turn it over to questions.